recording.
I mean, I have never met Ivan in person, but so he is a specialist in spectral asymptotics, which is an important subject, important, for instance, for quantum field theory on curved space-times, and for geometry and really many interesting things. And so I know Ivan actually from his book about heat kernels. And this is a very readable and nicely written book, which I recommend. And so I'm looking forward to his talk. Ivan, please go ahead.
Okay, so thank you very much for invitation. I'm really glad to do this. Well, I haven't done this. I didn't go to conferences for a long time due to pandemic. So this is the first time. So thank you. And it is nice to meet you, Jan, and everybody else. Well, I could say in person because I see you. So you're talking about my book. Well, I have another book. It's started like after I give some talks on financial mathematics in Paris. It's called Heat Kernel Method and its Applications, published by Birkhäuser. And another book is coming. It's accepted. It probably will appear next year. It's about heat kernel on symmetric spaces, on spheres and hyperbolic spaces and things like that. So it's a shorter book, but it's kind of narrow. But it's coming. Now let's go to the talk. So as you mentioned, I worked in spectral asymptotics and of differential operators, manifolds, and so on. Well, let me tell you a little bit of history. I was educated as a physicist, so I'm a theoretical physicist, and I was doing quantum field theory and quantum gravity and all that. And then pretty soon I realized that what is needed is to compute what is called the effective action in quantum field theory, to compute the green functions and other things. And they lead to the so-called heat kernel method. And this was due mainly to De Wit and his advisor Schwinger and other people. And then I started doing that, and then slowly but surely I kind of became first mathematical physicist and then mathematician, and now I teach mathematics. So the heat kernel is a very powerful method that studies spectral properties of operators on manifolds and vector bundles. And it's important in quantum field theory, as I said, statistical physics. And also when you do spectral geometry, for example. And that is the question that was asked a long time ago, whether you can hear the shape of the drum. In other words, given a spectrum of a differential operator, can you recover or determine the geometry and topology of the underlying manifold? So that was a very important question. And then the construction of isospectral manifolds became a thing. So it's a special area in mathematics. Also, it found applications in topology, in Atiyah-Zinger index theorems and things like that. So very nice and beautiful applications due to Atiyah, Patodi, and Gilkey and others. Also, it's related to so-called infinite dimensional Hamiltonian systems, integrable systems, and other things. Of course, in applied mathematics, the heat kernel of just heat equation, diffusion equation appears everywhere. And particularly in financial mathematics, it appears as a tool to study the derivatives like options and futures and mortgages and things like that. It started with the Black-Scholes equation, but now it became much more. And there is a whole literature on that subject as well. So that's the motivation for the study of the heat kernel. The goals, and I hope that to be able to cover this subject today, is to study spectral asymptotics of differential operators, and we'll start with natural operators. These are operators that appear naturally, so they are constructed from the geometric data like metric and connection and things like that. And these operators, so the most important ones are of Laplace and Dirac type. And then depending, well, there are some classical canonical setup, and then there is some generalized setting. And these include non-classical boundary conditions, which could be mixed or even include tangential derivatives that we call oblique boundary conditions, or even discontinuous boundary conditions. So these are all non-standard cases. And then sometimes you go to even more general situation where you consider non-Laplace type operators. These operators appear in particular in gauge theories, in quantum field theory, also in quantum gravity and other things. So these operators are elliptic, but they don't have so-called scalar leading symbol. I will talk about this later. But these are more general operators than Laplacians. Another thing that we've done with my student is non-perturbative spectral asymptotics. That's when you can do, well, assuming certain things about the curvature, you could actually sum up it in certain sense and do kind of generalized spectral invariants. And so I'll explain later what it means. And then, well, it turns out that in particular in spectral geometry, the spectral invariants, the usual ones, don't really determine the geometry. And so you may decide to study more general invariants that depend not only on the spectrum, on the eigenvalues, but also on the eigenfunctions. And these are more general invariants that you can define and study, and also study the asymptotics. And they include information that is not included in the standard ones. And recently I studied, like also with my students, like what I call heat determinant and quantum heat traces. These are traces not of heat semigroup, but more general function, and appear naturally in statistical physics and quantum theory and so on. And also in quantum field theory, there is a thing called, well, when an operator depends on time. So you have an operator, and then it changes from one operator to another operator. So you have time-dependent operators. And then this leads to so-called creation of particles in quantum field theory. And the invariant that determines it includes two operators. And so now you need to study the relative spectral invariants that depend not just on one operator, but on two operators. And of course, they are just arbitrary. They may not commute, and they could be pretty arbitrary in general. Well, and lately I'll show you how this can be applied to a particular case on so-called Weil algebra. Well, that's can be solved exactly. That's why it was a neat project. Okay, let's start with the beginning. So we can see the compact Riemannian manifold with some metric n-dimensional manifold. It could have a boundary. The boundary is assumed to be smooth. We can see the vector bundle over that manifold. Then, of course, we look at the space of smooth sections on that vector bundle, define an inner product, the standard inner product. And then if you, of course, the space of smooth function is not complete. And if you complete it, you get a Hilbert space. So the L2 Hilbert space is the completion of the space of smooth functions. Here, the volume, well, this volume, oops, sorry, well, when I click it, jumps, okay. That is the Riemannian volume element defined with respect of the Riemannian metric that was given. And the brackets include the fiber inner product. So you have a vector bundle, it has typical fibers. So this is the fiber inner product, and then you integrate it over the manifold. So here are the types of operators that we consider, and they are pretty general, generic ones. So D is the first order operator, and L is the second order operator. And I've written it in a form so that L is kind of formally self-adjoint. If the coefficients satisfy this condition that are written at the bottom of the page, And so these coefficients are pretty much arbitrary tensors, and these tensors takes values in the endomorphism bundle of the vector bundle. So roughly speaking, these are matrix valued tensors acting on vectors, right? On smooth sections of that vector bundle. And so in particular, the leading one, A mu nu, that's this tensor that is supposed to be symmetric and self-adjoint, but it's not really equal to the metric. So it's pretty much arbitrary so far. Then you look at the leading symbol of that operator, which is defined by this tensor. Here, psi is a covector in a tangent space, and so it defines a matrix or endomorphism H that depends on the point of the manifold and a covector. And then, depending on that, well, we'll assume that this is a positive definite matrix to make it elliptic operator. So this A mu nu, even if it is not symmetric, it is such that the leading symbol is positive definite. Then the operator is called a Laplace type if it has scalar positive leading symbol, which means that this leading symbol is proportional to the unit matrix, and then the coefficient, the tensor A mu nu, can be just identified with the metric G mu nu. So in general, of course, it is not equal to that, but in this case, given such an operator, Laplace type operator, it immediately tells you what the metric is. So in other words, the leading symbol of a Laplace type operator determines the Riemannian metric on the manifold. But in general, if it's not Laplace type, then there is no Riemannian metric in general. So, and if this is so, then it can be brought to this form that is written here at the bottom. So where delta is the Laplacian and Q is some potential term, which is some endomorphism. Well, this can be brought to such a form by redefining the connection. So once you identify the metric, then you modify the connection, and then it will take this form. And in local coordinates, the Laplacian has this particular form where G is the determinant of the metric and G mu nu with the alpha indices. This one is the inverse metric, and A is the connection one form, which of course is a matrix valued vector. The first order operator D is of Dirac type if this operator D star D, where D is the adjoint of that, is a Laplace type operator. So if you take this first operator multiplied by its adjoint, you get a second order operator. If that's Laplace type, then we call it the Dirac type. And then the coefficients will satisfy this equation, which of course is nothing but the Clifford algebra for those. The leading symbol of this operator, here it is D. So this gamma mu will be matrices satisfying this. And of course, physicists would call it Dirac matrices. They said, well, the Dirac matrices differ by I, by the imaginary unit from that. Okay, so now let's go to the boundary condition. So so as I said, we assume that it's smooth n-1 dimensional submanifold. We take the vector bundle V and then we restrict it, so we call it W. So W is the restriction of the vector bundle to the boundary. Well, if it's smooth, then there is a well-defined unit normal, we call it N. So assume it's inward pointing. Then we define the boundary data map. So in other words, you take a section of the vector bundle, smooth section, and then we restrict it to the boundary and also to to take the normal derivative, restriction of the normal derivative on the boundary. And so we put it all together and we call it boundary data map. So in other words, the boundary data consists of the values of a section and its normal derivatives at the boundary. And then the boundary condition have the form that there is some operator acting on this equal to 0. So where B is some boundary operator that acts on this. And of course, it has to satisfy certain conditions to be elliptic that I'll talk about later. Let me define a big class of this, which are called Gilkey-Smith group boundary operators. So they can be defined as follows. So we define self-adjoint first order tangential differential operator lambda of this form. So here, nabla hat is the covariant derivative along the boundary. So these are tangential derivatives, covariant derivatives. Gamma is just some coefficients, no relation to the previous gamma that appear in the Dirac operator. They could, but in general, these are just arbitrary, independent. And they're supposed to be anti-self-adjoint vectors. And S is just some, well, matrix value function. Let P or pi be a projection of this vector bundle. And then we define the boundary operator B as follows. So there is 1 minus pi, then 0, and then there is that. So basically what it does, it takes the projection and decomposes the whole vector bundle W into 2 subbundles, and then there are different conditions. One is put to 0, and another one you apply lambda, the operator lambda to that and put it to 0. And in special cases, like if the projection is 0 and lambda is the identity, then this is nothing but the Dirichlet boundary conditions that amounts to setting the boundary values of a section to 0. The Neumann condition is when pi is identity and lambda is 0. That's where you set to 0 the normal derivatives of a section. And Mix-Robin condition is when lambda is not the differential operator, but it's just endomorphism S. In other words, it's not a differential operator, but just a matrix valid function on the boundary. So, and again, mixed because you still split the bundle into subbundles. So that's the general, pretty broad boundary operator that includes a lot of cases. Now, in general, the boundary could be disconnected, like in this picture. So here is a manifold, and the boundary consists of 3 disconnected pieces, like sigma 1, sigma 2, and sigma 3. Well, in general, of course, it could have more. So these pieces are supposed to be compact manifolds without boundary, right? But they are disconnected, and this means that the boundary data map also decomposes accordingly to each of these pieces, and the boundary operator decomposes accordingly. Well, there is a type of the boundary decomposition. The T is missing here. Okay. So, and that means that this boundary operator on different pieces of the disconnected boundary could be different. For example, on sigma 1, you could impose Dirichlet condition. On sigma 2, you could impose Neumann conditions, and that will be fine. This will be still smooth boundary conditions, and there will be nothing wrong with the whole general structure of that. But it could be more general situation than this. Let me show you an example that I was taught by, I believe it was Peter Gilkey who showed me this example. So here is a problem. Assume that you have an iceberg in water, like this iceberg is this ball floating in the water. So half of it is underneath the water and another half is in the air above the water. And then, of course, if you're a physicist, you would impose different boundary conditions below the surface of the water and above the surface of the water, because the water acts as the thermostat. So you would fix the temperature at the boundary, and the air acts as an insulator. And so you would assume that there is no flux, and then you would impose Neumann boundary conditions. So, and if you do that, then and this interface between water and air, there will be a singularity. There will be, you see these black points. That's where the water meets air, and that's where the boundary operator discontinuously changes from one type to another type. And this is not smooth boundary condition. This is pretty interesting case, also numerically, if you try to do it. And so in general, this is a situation can be described as follows. So you look at the boundary, and you suppose that it's a disjoint union of, like in this case, sigma 1, sigma 2, and this compact submanifold, sigma 1 and sigma 2, with some boundary. And they have the same boundary. Of course, they are oriented differently, but the boundary of this sigma 1 and sigma 2 is the same, and that is sigma 0. And sigma 0 is a compact submanifold of codimension 2. So it's n minus 2-dimensional submanifold, and now without boundary. So in a simple situation of that ball, it's depicted here. So above the water is sigma 1, below the water is sigma 2, and this red circle, that's sigma 0. That's the interface, that's this boundary. Okay, so that's in general, you could have situation like this. Notice that the boundary itself is smooth, but the boundary conditions will not be smooth along that singular submanifold sigma 0. And so the Zaremba boundary conditions formulated as follows. So you you choose Dirichlet condition on sigma 1 and Neumann conditions or Robin conditions of sigma 2. And therefore it is discontinuous across that submanifold sigma 0. So then, of course, you want to have an elliptic boundary value problem, and you should study that. And then, well, there is a definition and there is some condition. So an operator with boundary condition is strongly elliptic if the leading symbol is elliptic in the interior. And that, I told you what that means. It means that the leading symbol is positive at any point at any non-zero covector psi. And there is another condition that is called Lopatinski-Shapiro condition at the boundary. Roughly, it says that kind of local problem should be with the zero boundary condition at infinity has a unique solution. But applied to the boundary conditions that I described, it basically amounts to the following, that this boundary value problem with the Gilkey-Smith boundary conditions will be elliptic if the boundary operator lambda will satisfy this condition where T is the leading symbol of the operator lambda. So psi is the tangential vector covector on the boundary. Gamma, remember, that's the coefficients in that tangential operator lambda. So T is anti-self-adjoint matrix. So T squared is negative. So this is negative valued. And so basically it says if it's not too big, if the tangential derivatives are not too big, then this T squared will be negative and small, and then this will be positive, and then it's elliptic. If it is violated, in other words, if the tangential derivatives become big, then it fails to be elliptic, and then it will not have a unique solution. You'll see later what it amounts to. So it turns out that for the Zaremba problem to be elliptic, you need an additional boundary condition along the singular set, sigma 0. Without this condition, it is not really well posed. So there is some arbitrariness involved. And so, for example, you need to choose either Dirichlet condition on that set or some kind of Robin condition on that set. Here, rho is the normal distance to that singular set sigma 0. And S is, let's say, some real parameter. So if you set these conditions in addition to those conditions, then it is well posed, and then it will be elliptic. And then here is well, here is a standard theorem. It says that the operator L with positive leading symbol that I described before is essentially self-adjoint, and the eigenvalues are discrete, and they have finite multiplicities and form an unbounded increasing real sequence. And of course, there is a bottom eigenvalue, and then it goes to positive infinity. And the eigenvectors can be chosen in such a way that they form an orthonormal basis in L2. And so that's what you can use later to do spectral decompositions. Okay, so the question of spectral geometry, the whole idea is that the analysis is primary and geometry is secondary. So what it means is that if you're given a partial differential operator, then it determines, so it induces the geometry in some sense. So if you have a Laplace type operator, then it determines Riemannian geometry by its own leading symbol, because the leading symbol, of course, includes the metric. So if you take two derivatives with respect to psi, the covector, then you just get the metric. Well, if you take a non-Laplace type operator, then it's matrix valued, and of course there is no Riemannian metric. So then you could look at the eigenvalues of that, and the eigenvalues will be homogeneous functions of order degree 2 of psi. And then if you take two derivatives of that, it will define the so-called Finsler metric. So you will have as many as the dimension of the vector bundle. So and that's a very interesting problem to study, and I actually wrote several papers on that, trying to apply it to gravity, so-called non-commutative gravity and non-commutative geometry and all of that. So when the metric itself is doesn't commute with itself, then you basically get Finsler geometries. Okay, so can you hear the shape of a drum? Well, the answer to that question, of course, is no in general. Then there has been constructed isospectral manifolds, also continuous and discrete, such that they have the same spectrum. But then it can be generalized in the following sense. Okay, if you cannot determine the geometry completely, then at least what geometric information you can extract from a spectral differential operator. Maybe if you take more than one operator, maybe if you look not just at Laplacian, but at operators on different vector bundles, and then you look at the spectral data, maybe if you look at the relative spectral data, you could determine the geometry of the manifold. In general, the large eigenvalues, so the spectral asymptotics, determine the local structure of the manifold, the local geometry, and the bottom spectrum that determines the global structure, the topology of the manifold. Okay, just some background on the heat equation. So here is the heat equation with that operator L that I described before. It's just some elliptic operator with some initial condition, which is given, and some boundary condition with one of these operators that I described. Then the solution, of course, is written this way with, this is called a heat semigroup exponential of minus DL. That's an operator, like, bounded operator. And then it can be written in this form as an integral where U is so-called heat kernel. So that defines what heat kernel is. The heat kernel is the fundamental solution of the heat equation with the initial condition and its satisfying boundary conditions. So of course, the motivation for that is to solve the heat equation, but that's the heat kernel. If you know the heat kernel, you will know the solution to any of these problems described before. Well, if you know the spectrum exactly, then of course you can write the solution. Here it is at the bottom. It is the spectral sum over the eigenfunctions and eigenvalues. But of course, in general, you don't know this. And also on non-compact manifolds, you wouldn't have such a decomposition. The heat kernel has a well-defined heat kernel diagonal. That's when you take it at equal points. And that's an important tool. And so this is a smooth function. And then the heat trace, which is the L2 trace of the heat semigroup, it just is the sum of this e to minus t lambda k, where this is the spectral, the eigenvalues. And it's not that difficult to show that it's equal to the integral of the trace of the diagonal. So the heat trace is equal to the fiber trace of the diagonal of the heat kernel, and then integrated over the whole manifold. And then once you have the heat trace, of course, it will define the zeta function by the Milin transform. I put here also lambda, a complex parameter lambda for generality, so to avoid problems with the zero eigenvalues and things like that. And then once you have the zeta function, you could define the determinant, the spectral determinant, because the zeta function allows you to do analytic continuation in S, and then it will be meromorphic function, which is analytic at the origin at S equals 0. And so you could evaluate the derivative, and it gives you some invariant, and it, by analogy with the finite dimensional case, it is nothing but the determinant of that operator. So this is the definition of the logarithm of the determinant, functional determinant of elliptic operator. And of course, that finds application in quantum field theory everywhere. That's exactly what the effective action is in quantum field theory and in quantum gravity and things like that. Okay, so spectral asymptotics. So of course, you cannot really know in general, you cannot compute the spectrum exactly. So what you are studying instead is the asymptotics, is, as n goes to infinity, what happens to the eigenvalues. And instead of doing this directly, you study the short time asymptotics of the heat trace. So that gives you an indirect way to study the spectral asymptotics. And well, there is a general theorem that in general it has the following form. So here there is this factor 4 pi t to the minus n over 2. N is the dimension of the manifold. And then there is this asymptotic expansion in the half integer powers of t with some coefficients. And then in general, there is additional piece logarithm t and then another expansion. So that's the kind of the most general form. And then these coefficients, which are called the global heat trace coefficients, they have the following form. There is a piece which is an integral over the whole manifold, then the integral over the boundary, this is sigma 1 and sigma 2, and then there is an integral over the sigma 0, which is that interface of discontinuity. And HK, these are the coefficients that could appear because of the singularity along the sigma 0. So in general, these logarithm terms appear when you have some kind of discontinuity or singularity, or like if your boundary is not smooth, or even if your operator is not, if it is like pseudo differential instead of differential operator, things like that. So that's the general situation. Well, let me describe the properties of this. The interior coefficients, the AK, are local invariants that depend only on intrinsic geometry of the manifold, like curvatures and things like that. They don't depend on the boundary at all. The codimension 1 boundary coefficients, BK, depend on the intrinsic geometry of the manifold, but also on the extrinsic geometry of the boundary itself. And the codimension 2 coefficients, CK, they depend on the intrinsic geometry of the manifold, the curvatures, the extrinsic geometry of the boundary, but also on the extrinsic geometry of the codimension submanifold sigma 0. How does it sit in the boundary? So it will have its own extrinsic curvatures, and there are more than one. Then one can show that the volume coefficients of order vanish, so A2k plus 1 is 0. In other words, there are no half integer coefficients of this form that include half integer powers of t. And for manifolds without boundary, of course, all of the boundary coefficients are 0, so they don't appear at all. For manifolds,
could you recall what is sigma 1, sigma 2, sigma 0?
Well, here it is basically. So sigma 1, there is a Dirichlet condition, and sigma 2, there is a Neumann condition, well, roughly. And then sigma 0 that's where it jumps from one to another.
So these are Zaremba boundary conditions. So.
Yes.
Okay. Thank you.
Yeah, you're welcome. All right, and then if you have manifolds with boundary and smooth boundary condition, like if you have a disconnected boundary, and even if you have different boundary operators, but it's still smooth, then the logarithm coefficients are equal to 0. They don't appear, and then you have either Dirichlet or Neumann, then one of these is 0. Okay, so there is either this one or that one. If you have discontinuous boundary conditions, which are Zaremba boundary conditions, then in general, it could have these logarithm coefficients, but it has been shown by Seeley in a paper that we discussed at the conference, and he then went ahead and he showed that they don't appear. In other words, in general, one can prove that even for Zaremba boundary problem, there are no log terms in that expansion. So that's the general theorem. Okay, and then here are the results. Well, not the results, but the review of the results. So what is known about this condition? Of course, for the interior coefficients, a lot is known, and they are computed up to A8, which includes T to the power 4. Actually, I computed this in my PhD thesis almost 30 years ago. Well, in 87, I don't remember how it was. And then for boundary coefficients, there are many people. I'm not going to, review the literature, but many people contributed to that, and they computed these coefficients. For the oblique, which is more complicated, that includes the tangential derivatives. That's more difficult case, and there's still some of them known. For the Zaremba, again, I computed this coefficient sigma C2, the first non-zero coefficient. For non-Laplace type operators, that's much more complicated case, and then a couple of first coefficients were computed in general, and for boundary conditions, there is just one that was computed.
Non-Laplace, but still second order.
Yeah. So, yeah, we don't consider anything higher than that. Yeah, the second order operators. Well, I've written a paper on higher order operators, but they were powers of the products of the Laplace type operators. So if you have several operators, which I'm not talking about this in this talk, you have several Laplace type operators, and then you look at the product of those, then you can actually derive many things, but I'm not going to do it today. There is a paper that I wrote in 1998, I believe. So how do you compute these coefficients? Well, there are many different ways, and people apply different tricks, but so here is the most general and direct way how to do it. So you basically you decompose your manifold into different regions, and then you construct local solution in each one separately, and then you asymptotic solutions, because you only want to do it for as t goes to 0. And then so one is the interior manifold, which is far away, not far, a little separated from manifold. Then there are these shells close to the boundary, M1 and M2, which are close, like within the epsilon distance. And then there is, on the boundary, there is a strip which is close to the singular submanifold sigma 0. And so you could do that all separately, and you consider this, and then you, of course, you have to integrate over the whole manifold. So this is what we do. You decompose the manifold in the following form. And so I described this narrow strip with some epsilon, and then on a finite distance from the boundary. And M0 is a piece of the manifold that is close to sigma 0 on some epsilon from that. And then you look at this geometry, and it's kind of beautiful geometry of this manifold sigma 0. But then you will see that there is this geometric information, that there is normal to the boundary, and then there is extrinsic curvature. But when you look at the sigma 0, then there is not just one normal, there is a whole normal bundle. So there are two normals, and then there are two extrinsic curvatures, and they all, of course, enter into the picture, into calculation. And so how do you do it? You construct different approximations in different domains. You glue them all in a smooth way, and then you control the remainder and it depends on epsilon, and then you compute asymptotics in each set separately, and then you take the limit as epsilon goes to 0. And it turns out that those solutions that are close to the boundary and to this piece sigma 0, they behave like delta function, like a distribution. And when you make that distance go to 0, epsilon go to 0, then you get it. When you integrate it, you get this contribution because of this delta function-like behavior, and that's where the origin of those terms in the asymptotic expansion is. So for the interior parameter, this is what you do. You rescale your coordinates, you fix a point, then you construct a solution close to that point locally, and also for small t. So you take, well, this is kind of general scheme. You do this, you operate, it becomes depending on epsilon, you expand it, and then there is a corresponding expansion of the heat kernel, and then you put it in the heat equation, you get, recurrence relations, and then you solve it one by one, and then you get these coefficients, and then you look at the diagonal, take the trace, and that gives you this spectral invariant. So that's kind of how you could do it, but nobody, of course, does it this way, but that's how you can do it. For the Laplace type operator, there is this semi-classical ansatz, which is obtained by doing what is called singular perturbation method, which means that the interior heat kernel basically looks like this, where there is this exponential of d. D is the geodesic distance between these 2 points. And then there is some expansion. So if you substitute this into the heat equation, you will get a differential recursion relations for these coefficients alpha k. You expand them in the Taylor series, and then take the diagonal values, take the trace, and that will give you the those coefficients as well. And that's how you could do it much more effectively. For the boundary term, it's more complicated, of course, but this is what you do. You let R be the normal geodesic distance to the boundary, and x hat be normal coordinates on the boundary. You fix a point on the boundary. Then you replace it. You consider that R, the normal distance, goes from 0 to infinity. So you basically blow it up, the neighborhood, you blow it up to infinity. Then you rescale these coordinates accordingly. And then you do this expansion of that additional piece. And then, well, and then you have to solve some differential equation actually in this normal coordinate. And then you take the diagonal value. And when you integrate over that piece, over this M1 boundary, that amounts to integrating over the boundary sigma 1. And then this thin shell in the normal distance from epsilon to 0. And that, when you take the limit as epsilon goes to 0, that will basically, this integral will give you the contribution of an integral over sigma 1, because that behaves like a delta function. So that's pretty much how you do it. And the Neumann parametrics for sigma 2 is done similarly, but of course then there is a boundary operator, and you have to scale it as well, because it also depends on epsilon, and a little bit more complicated, but you can also do it. Now for the Zaremba operator. So here is the situation on the left. So you blow it up, you pick a point here now on this submanifold sigma 0. And so on the right, this is like scaled version of that. So here is the red, the red one is the sigma 0 submanifold. The upper one is the sigma 1, the low is sigma 2, n is the normal, inward pointing normal. R is the normal distance to the boundary. And y here is the distance along the boundary to the sigma 0, to the codimension 2 submanifold. So I hope it is clear. So R is the distance from X to the boundary, and Y is the distance within the boundary to sigma 0. And Y is signed because it could be from above and from the bottom. So it's a signed distance. So here is the setup. X hat are normal coordinates on sigma 0. I is the normal geodesic distance to 0. Y is the sine normal geodesic distance to sigma 0 along the boundary. And then on that, you could introduce polar coordinates in the normal bundle, which is defined this way. And of course, theta is an angle that goes from minus pi/2 to pi/2. If you look at this picture, theta goes from this point to this point. So it's only the right-hand side of this picture. So that's why theta has this range, the angle, the polar angle. And of course, that means that r is positive and y could be positive in sigma 1 and negative in sigma 2. So you do that, and then you replace this piece by this manifold, so that it's sigma 0. R is basically, that's the y range. R plus is the r range. And then you do the scaling again, and then you expand it in epsilon, and then you will have to solve a one-dimensional mixed boundary value problem in the angular coordinate, because on theta here, on sigma 2 in theta, you'll have Neumann conditions. On sigma 1, you'll have Dirichlet condition. So you'll have one-dimensional operator with mixed boundary conditions at the endpoints of theta. And so once you solve it, and then you do expansion in epsilon, the rest is the same. You get differential recursion relations, you look at the diagonal. And then when you integrate it, you'll get an integral of this form. So it's integral over sigma 0, integral over the geodesic distance to the boundary. Well, there is this extra power of rho, because this is the geodesic distance to codimension 2 submanifold. And then the integral over theta. And so all of this will go away, and when epsilon goes to 0, you end up with an integral over sigma 0, and that gives you the coefficient sigma k, ck. So that's how it can be done. It's kind of time consuming, but that's the calculation. And so here are some results. Well, these are well-known results. This is nothing new. For Laplace type operators and mixed boundary conditions. So the A0, of course, is determined by the volume of the manifold. The A1 is, well, it's the integral over the boundary. This is the trace of that projection operator, if you recall what it was. And A2, this R is the scalar curvature, Q is the potential term, K is the extrinsic curvature of the boundary, and S was coming from that potential term in the boundary operator lambda. And of course, there are other terms that I don't want to write, they are more complicated. For the Zaremba boundary value problem for Laplace type operator, here is the A0, of course, is the same. With A1, you see that there is this difference of the volume. And that's because they have different boundary conditions for Dirichlet and Neumann. And for Dirichlet, you have negative sign. For Neumann, you have positive sign. That's why there is a difference. So in particular, if the volumes of those are equal, then A1 will be 0. And then the A2, of course, has well, kind of the same form. And then there is this additional piece, and that is proportional to the volume of the sigma 0 coefficient, the singular submanifold of codimension 2, with some coefficient, and that coefficient depends on that extra boundary condition for the Zaremba type. So if it is Dirichlet condition, it is -1. It is Neumann type condition, then it is 7. Well, there was some controversy about this coefficient because different people compute different values. There was a conference that was discussed, and we then we cleared it up, and then we found that you need this additional condition. It turns out that it depends on that additional condition. Okay.
When was it? When was this conference?
Well, this conference was in Naples. I was a key speaker. There was Seeley, there was Grub, there were Gilkey, there were Wojciechowski. Many people were there. Was 99, I believe, maybe.
But Zaremba, as far as I know, I mean, lived much earlier.
Yeah, well, Zaremba is just a name. I mean, that was a long time ago. I mean, Zaremba is just, he came up with that much early. I mean, we were talking about the asymptotics of the heat kernel for that type of condition, and different people like Dowker, Stuart Dowker, and Klaus Kirsten, and many others, and Peter Gilkey, and so they kind of got different values, and it turns out that it depends on what happens at that singular submanifold. So, well, if you're interested, I have a big paper on this subject. It's called, by the way, it's at the end of these slides, at the end in the references paper in Mathematical Physics, Analysis, and Geometry in this journal on that. And then there is a whole history is there in that paper. Okay, so for oblique, you have Laplace type operator, but the oblique boundary condition. Well, A0, of course, is the same, but the A1 is already complicated because that's the first boundary coefficient. It has this extra term, little gamma, which is given by this integral. And that includes that t squared. T, remember, that was the leading symbol of the tangential operator lambda. And I told you that it's elliptic if this t square is not that big. Well, if it is positive, then this integral would diverge. If it fails to be elliptic, this integral diverges, and then then you don't get anything. So it only converges if the problem is elliptic. In other words, if t square is negative but not big enough. So, well, you could compute it in a particular case. Let's say if gamma is 0, of course, then this integral is easily computed. It's Gaussian, it's just then. If the matrices commute, that's a trivial case, then here is how it looks. If the matrices form the Clifford algebra, so it's like a Dirac type operator, then this coefficient has this form. And you see that if kappa is more than 1, you get a singularity. So that tells you that it fails to be elliptic. In other words, this will be finite only if kappa is small, if gamma is not that big, because otherwise it fails to be elliptic, and then the asymptotics are not even well defined. Now, for non-Laplace type operator, let's say you have an operator of this form where A is not really the metric, but some matrix. Then it can be computed as follows. So you compute the diagonal, the heat kernel diagonal, and you can write it as this integral. Like if you write the delta function in terms of Fourier, then it will be equal to that. And then you modify it as follows. You say, well, this L is that differential operator. Then by acting on these exponentials, it is equal to the sum of 3 operators. So H is the leading symbol, L is the given operator, but K is the first order operator, which is defined this way. So it's a first order operator with psi is the cotangent vector. And therefore, this exponentials, they boil down to this exponential of again, H is a leading symbol, so it's a 0 order operator, K is the first order operator, and L is the second order operator. And then you rescale this psi by square root of t, and then it becomes this. And you see here, H doesn't depend on t, and there is square root of t in front of K and t here. And that can be expanded in powers of t as t goes to 0. And if you do that, of course, these things in the exponent don't commute. But if you use the formula, what is called the Volterra series for the exponential of non-commuting operators, then, and you expand it in powers of t, then that will give you the asymptotic expansion of the heat trace in powers of t. And that's what you look for. And this is what you'll get. So the 0 order coefficient is equal to that. By the way, there is no boundary. That's why this is A1 is equal to 0. So you see that this is the exponential of the leading symbol, and then there is a trace, and then an integral. So if this would be Laplace type operator, then this whole thing will just give you the determinant of the metric, and that is just the volume of the manifold. But for non-Laplace type operators, that's all it is, and you cannot really specify it further. And the next coefficient is equal to this, where there are this exponential of the leading symbol, and k is the first order operator, and L is the second order operator. And so you have this expression. Well, it can be simplified further, but I don't really want to go to this. But that's the answer. Here it is. You know, it's just written in a way. Of course, if this is a Laplace type operator, then this will boil down to the scalar curvature. This would be equal to 1/6 of scalar curvature. But in general, it is just some derivatives of the leading symbol and other things. For the interior coefficient, for the boundary, so if there is a boundary, let's say you have Dirichlet boundary condition, then it's even much more complicated because the leading symbol is not commutative. So here is the first coefficient looks like this. So it's an integral over the boundary, then there is an integral over the cotangent space, and then there is an integral over the complex parameter lambda, and then there is this derivative logarithm determinant of phi. What is phi? Phi is this integral where h is the 0. Well, that's the leading symbol evaluated at the boundary. The 0 means that the distance to the boundary is 0. So the leading symbol at the boundary, you decompose the tangent vector, cotangent vector at the boundary. So omega is the dual to the, well, it's the first component of the covector. And so anyway, this is this integral, then you take the determinant, then you take the logarithm, then you take the derivative, and you integrate. It's a pretty complicated expression, and that will give you this first coefficient. And of course, it only depends on the leading symbol of this operator at the boundary. So for non-Laplace type operators, it's much more complicated because there is no really machinery of differential, like Riemannian differential geometry, that enables you to write it in a much more compact form. Okay, so the next subject I want to talk about the so-called non-perturbative spectral asymptotic. So now
so it's almost 1 hour. So that just
yeah.
I'm enjoying it very much, but perhaps you should think of.
Yeah, let me wrap it up. Yeah. Well, I will. Well, if you, which part of it? Well, let me just show you some new stuff. Well, you could define, well, an invariant like this, which I call heat determinant, where you see that it depends on the eigen functions as well. And that's much more general invariant than just the heat trace. And we were able to find its asymptotic expansion and compute some of its coefficient spectral invariance. The other heat traces I want to talk to you are this. The trace of minus beta, where omega is square root of the operator, that's called the relativistic one. And then these traces that I call the quantum heat traces. And as beta goes to 0, we also computed its asymptotics, like, you know, we've done that as well.
So asymptotics in beta or
in beta, yeah, because beta is the well, it's the inverse temperature, and that's the one that kind of generalizes it. And of course that comes from physics, you know. And so as beta goes to 0, that's called the high temperature asymptotics, and that's what you So this is computed, and by the way, there are papers at the end of these slides, and I hope these slides are available. That's, if you're interested, you can look it up. And then well, there are invariants like this at the bottom, and they can be boiled down to traces like this, where there are two operators. And these are called relative heat traces. You see that there are difference of heat traces, and then the products of heat traces, and the D is the Dirac operator, so for Dirac operator as well. And so we define these combined heat traces X and Y for the product of semigroups, and then we computed the asymptotics of those. And of course, now there are two time parameters, T and S, and so we've done that, and then it shows how we could do it. Well, and the last was when you have two sets of operators that form the following algebra, and R plus R minus are kind of curvatures. They call it curvatures. So if you have these two operators, two sets of operators, then you define two Laplacians, and then you can prove that there is this representation for the product of semigroups, and then you can compute the kind of the generalized heat kernel. So there is a formula for that in terms of the matrices that are defined by these curvatures. But these
are Gaussian. I mean, these are essentially exponentials of quadratic Hamiltonians.
Yes. Yeah. So each one of this is, the heat kernel for each delta plus and delta minus is like, well, it's based on this formula. Here is the formula.
Yeah. So it is exactly solvable.
Yeah, and then when you have a product, you could use that formula, and then you have some kind of Campbell-Hausdorff type of formula, and then you get this, and then you can come up with the final thing. So that's for the product of two. There is T and S, and it's still Gaussian, and it has the following form. And so the last I want to show you, well, if you're interested, here are the list of papers. And the paper that I was talking about is that, well, non-Laplace type operators, and then you see here heat kernel for Zaremba boundary value problem. Here is the reference for that paper. Well, that's all. Yeah, as I said, we'll talk as much as time allows. So, any questions?
Thank you. So, questions or remarks? So I have the following question. You were speaking about diagonal elements of the heat kernel. Now, what about behavior around the diagonal of the heat?
Okay, so you talk about off diagonal. Well, this is known a little bit. Let me show you a formula. Just wait a second. Here. So, well, here, this is for off diagonal. So this is not on diagonal, but here are the coefficients alpha k. Well, this can be computed in form of a Taylor series as x approaches x prime. And the algorithm for that is explained in that in my thesis and in my papers and in that book that you mentioned. So you could compute as many as you need terms, but this is basically in the form of a Taylor series as expansion in x minus x prime, roughly speaking, or it's a better way to do it in normal coordinates around the point. You fix a point x prime, then you choose normal coordinates, and then you could expand it. And so there is a very effective algorithm how you could do it. And so there are some explicit expressions for like A2 and some derivatives of that, but So you can do it, but not that many people interested in that, but it's possible. For without boundary. With boundary, it's much more complicated. You have to do those solutions, but they will only be valid near the boundary. So there is a solution explicit type, even before you integrate it. It's written in those papers that I mentioned, but it will not look like this. There is a kind of well, it includes some error functions and some special functions and things like that. So, but you can do it in the narrow strip near the boundary. You can also do off diagonal one. When you put it on the diagonal and integrate it, then you'll get the spectral invariants. Otherwise, you end up with this.
Yeah, another question. What about the asymptotics of the Green's operator? I mean, the inverse or the resolvent of the.
Yeah, well, the resolvent would be like a Laplace transform of this. So if you again, I didn't talk about it. There is a paper of mine, which is in Journal Mathematical Physics in '98, that lists exactly the expansion. So it will be there is an expansion. It's called Hadamard expansion, and it will be determined by the same coefficients, heat kernel coefficients. At least the singular part is determined by that, and then there is some extra stuff that's kind of global and not determined, but a lot of it is determined by the same coefficient. So pretty much what you do, you have this expression, you multiply, you do the Laplace transform. It's like E of t lambda and integrate over t, and you integrate this expansion and you'll get it. So, and then the asymptotic expansion would be in the powers of lambda of the resolvent parameter as lambda goes to infinity, to negative infinity. And so, I mean, this can be done based on this expansion.
Yeah, but you mentioned that there is an extra stuff. So what?
Well, let me see if I can find it, and then try to share it with you. Let's just, if you're really interested, let me just wait a second. Papers, journals, physics. Can I stop sharing this and
Yeah.
share something else? Okay. Just wait a second. No. Yes, that's it. Okay, yeah, there are so many windows open. Here it is. Do you see it?
Yes.
Okay, so where does it? Okay. Well, here is the expansion of you see it says here the green function G, the equation 29. Do you see that?
Yes.
Okay, so it has three parts. There is singular part, non-analytic part, and then there is regular part. So the singular part, you see here, it has this expansion, and there is AK. This is equation 30. This AK are the heat kernel coefficients. And sigma is this geodesic distance of the world function. The non-analytic part and the regular part, they have this expansion. So again, this is the AK, that's the heat kernel coefficient, but there is this additional piece, it's called B. And that B, that's a non-local stuff, and that's a non-singular stuff. So, well, here, look at the equation 32 and 33. So what is called B, that's, well, that comes from the Milin transform of the heat kernel, but it's not locally computable. That's a global stuff. And of course, it depends also on dimension, even or odd dimension. But that's how it looks. So there is a certain piece that is there is an expansion that has the same coefficients as the heat kernel. This is what's called AK, and then there is a different additional piece, and that contains stuff. And that stuff is non-singular. You see, it has positive powers of sigma.
All right. So
Sigma,
it is smooth.
Yeah, it is smooth. Yes, yes. So sigma is the distance. So this is a smooth part, and in the even dimensions, there is a logarithm term. You see, here is the logarithm of sigma. That's the singular part. The singular part is always the same. It will be determined by the same coefficients, heat kernel coefficient, AK. The smooth part, that's the other lines of this equation 34. That includes this BK, and so this is the stuff that is smooth. Okay, here it is again. So this is in even dimensions. Equation 35 and 36. So you see the non-analytic part, there is logarithm sigma. That's singular, and that's determined by coefficients AK. And the smooth part is determined by B prime, and that's the global stuff. That's not locally computable.
Okay.
So the short answer is that the singular part and non-analytic part will have the same coefficients as the heat kernel coefficient.
Okay, thank you. So if there are no other questions.
Can I ask a naive question?
Yes.
Yeah.
Simple. Yeah. So this is about this iceberg boundary condition. So
Yeah.
I guess that many physicists did naive numerical calculation of this situation without thinking very careful about this extra boundary condition that you need on this sigma 0. So in that case, do they meet any pathology or something like that?
No, but usually people implicitly assume one of those, you know. Usually they would assume that it's because there are these two, that there is this Dirichlet and Neumann, and you either extend Dirichlet on that singular part, or you extend the Neumann condition on that singular part. And usually people implicitly assume that it's one of this. Like you could, instead of this, you could consider, for example, a box. Let me try to do something. Okay, do you see page? Yeah.
Yeah.
Let's say you have this box, right? And you would have different conditions, like you would have Dirichlet here and Neumann here. Okay, then this would be the singular stuff. And physicists do that all the time, right? So here is just a cube, that's easy. But then it depends what you assume on that red stuff. And so usually you just, when you do separation of variables or something, you implicitly, without thinking of it, you assume certain thing here. It's like you do it, but you don't really write it. You don't really think about it. But if you're more careful, then you need to specify it. And then there is this additional, well, as I said, if you do it one way or another, you will get different things. And if you go to that paper that I said at the last, at the end of the slides, then it talks in all details about this and why there is this, arbitrariness and how it is fixed, and depending on what condition you choose, you get different solution. It's just different solution. In the neighborhood of that, if you just choose this, so in the neighborhood of this, there will be different solution depending on what you assume happening on that interface.
Okay.
It's
Yeah.
some
thank you.
kind of leakage, it's either one thing you assume that it is non-penetrating, or another thing you fix that coming from this Dirichlet plate. But it has to be specifically applied. When you do Eric, you don't really think about it, but it's actually happening.
So are there any more questions or remarks? So I don't see.
Oops.
Hello?
You said the chair is gone. So anyway, okay, yeah. Let's thank Ivan again. Thank you very much.
Thank you very much.
Thank you. I hope you find something interesting.